So we will go ahead and get started. So welcome everyone. Tom, thanks for the introduction, and thanks for giving us the opportunity to come here and tell you about our perspective on the GPODS project. Again, my name is Jerry Warchel. I am a manager with Dominion Energy, and I am the responsible manager overseeing the technical aspects of the GPODS project. Tell you a little bit about myself. I'm an electrical engineer by trade. I've been with Dominion Energy for 15 years. I've worked in all three of our kind of core function business sectors. I was a electrical systems engineer in our nuclear plant, North Anna Power Station. I worked in system operations for 5 years, where I was a certified PJM bulk electric system operator for 5.5 years. And then I am now in distribution, having a lot of fun with battery energy storage systems and renewable energy. Okay, so the agenda for today's talk, we're going to start out with some basics and talk a little bit about battery energy storage systems. We'll go over some definitions and components for those that may not be familiar with them on the call. And then we'll talk about why energy storage is important to utilities. We'll then get into Dominion Energy's storage goals as we continue to decarbonize the bulk electric system. And then we will cover one of our battery energy storage system pilot projects. And specifically because stationary battery energy storage systems, which are, what we've deployed thus far until the GPODS project, are very, very similar to the GPODS. Then we'll get into the GPODS project. We'll talk about some challenges we have to the project, and then we'll talk about where we're going with the project over the next 5 years plus. Okay, so a battery energy storage system, or BESS, as you will hear, is capable of receiving power from the grid and then storing it, and later on injecting it back to the grid. A BESS consists of a power conversion system, and that's probably the most important piece of the system. That's what takes the direct current that's stored in the batteries, and it inverts it to become alternating current for injection out onto the grid. That power conversion system also takes alternating current from the grid and it rectifies it to become direct current for charging the batteries. The system also consists of the battery packs themselves, a battery management system. That's essentially what is monitoring the batteries to make sure that the individual cell voltages are balanced, the charging is happening properly, and temperature is controlled in the system. A controller itself, and that controller is the brains of the system, telling things when to charge and when to discharge. A thermal management system to exhaust the heat that is associated with charging and discharging, and then monitoring devices. In electrical power systems, we always have monitoring devices to make sure things trip offline when they're supposed to trip offline. The smallest component of a battery system is the cell, and that's the picture in the left-hand side. They don't look much different than the cells that you see, for a flashlight, maybe a little bit bigger. Each of them are typically about 2.7 volts DC, and we string those together in parallel and series combinations to make about 1,000 volts DC, and that's how we end up, feeding that to the bidirectional inverter, also known as the power conversion system, to discharge out onto the grid. The cells go together to comprise a module, and then the modules get put together in what's called a battery pack. So you see an exposed version of one of our systems there. Those big squares, are the packs themselves. And then all the packs go into a big container that looks like a Connex box or a tractor trailer, and that's the battery system themselves. In that case, we're looking at a Tesla Megapack. And by all means, and during the presentation, if somebody wants to chime in, just please go ahead and stop me. I'll ask Tom to watch the chat because I really don't have eyes on that if something comes up and you guys want to stop. So we'll get into why energy storage is important to utilities. And the first point I'd like to make is we first need to understand a little bit about Dominion Energy's generation portfolio. And this really doesn't look much different than any utility's generation portfolio. And in the last 10 years, we've seen a lot of changes. As a result of decarbonization, we are seeing lowering percentages in traditional fossil fuels like coal and oil, and we're seeing an uptick in renewable energy. And renewable energy itself, it creates challenges for how the grid was designed from the get-go. And we call these resources intermittent resources. I'm sure you've all heard the sun doesn't always shine, the wind doesn't always blow. Well, that creates a problem for the bulk electric system. And the reason being is because at any given time on the system, the power has to be matched. The power injected on the grid has to be matched with the consumption. If it's not, really bad things happen, like blackouts. Well, that's where energy storage comes into the rescue. So during those intermittent times, that energy can be stored and then it can be dispatched to make sure the grid is operating just like it was designed in the past. Let's dig that apart a little bit more. So let's focus in on the graphic on the right-hand side, the PJM geographic footprint. So you'll see Dominion Energy there in green, outlined in the state of Virginia. Dominion Energy is part of the PJM RTO. And what that is it's a power pool. We are connected to all of our adjacent utilities with tie lines, and we share power with them. Power is bought and sold on the market every day, just like stock. And at any given time in PJM's territory or the entire grid worldwide, there's a load curve. And the load curve is essentially all the power that is being consumed on the grid at any given time. And what you see, I have a picture here of PJM's typical summer load curve, and it looks very sinusoidal in nature. Okay, so in the early morning hours when everyone's asleep and the factories are offline, our load is low. So there's a low consumption point of power on the grid. But then as we start waking up during the day, factories start coming online, we essentially reach a peak. And at any given time, that power has to be matched, right? So we can focus in on the scale on the bottom of the slide. So the generation has to meet the demand at any given time in order to maintain the 60 hertz that our power system operates at. So generation is you got to understand a little bit more, right? So it's not just the generators are online, and this is why I brought the PJM geographic footprint into it. So generation, it's really all the power that is injected into our system has to meet the demand at any given time, the instantaneous demand. So that is all generators that are online, and that is all interchange coming into our system. So power that is coming from other utilities into our system. And then similarly, other utilities have to meet this too. So Dominion could be supplying, power to Allegheny Power, for instance, and their power has to be matched as well. And then the load, the demand is the load and the losses. So load, that's all the houses, that's all the commercial, that's all the industrial consumers that are hooked up to our system, that are pulling power off of it and consuming it. And then the losses is what is lost on the system to wheel power from point A to point B. So if I have a generator that is 40 miles away from Richmond, and that power is running down transmission lines going into Richmond, Virginia, there is power that is lost on those transmission lines through heat as the electrons circulate through the resistance of the lines that turns into heat. Similar to if you look down into your toaster and you see that glowing tungsten, that is watts lost, right? So in order to maintain the power balance at any given time to meet the PJM load curve, we have to have the generation equal the demand. If it doesn't happen, if I have too much generation and not enough demand, my frequency goes too high. If I don't have enough generation and I have too much demand, my frequency goes too low. And what that causes, it causes all of our AC running motors that are tied to the grid to fail. And it causes voltage to fluctuate up and down, and our sensitive electronics that are hooked up to the grid will also fail. So at any given time, we have to have that dispatchable power. So we can charge batteries looking at that PJM load curve during the low load hours, and then we could discharge the batteries during those high peak hours in order to have that stored power and control a good, steady profile of power on the grid. Okay, so that gets into why utilities, battery energy storage systems are important to utilities. Let's get into Dominion Energy storage goals. So Dominion Energy got into battery storage with passing of the Grid Transformation and Security Act of 2018. That called for Dominion Energy to install its first 30 megawatts of energy storage in our service territory. And at that time, we developed a pilot program seeking to improve reliability of our bulk electric system and our distribution system, also improving and increasing the integration of different types of renewable energy resources, deferring the investment of infrastructure, specifically generation, transmission, and distribution infrastructure. And then last, reducing the need of additional generation during times of peak demand at that peak point of that PJM load curve. So thus far, Dominion has deployed 3 pilot projects on our distribution grid, totaling 16 megawatts. Construction was overseen by Dominion's distribution team, specifically my team, and the generation department. But looking forward into the future, the Virginia Clean Economy Act is mandating Dominion Energy to install 2,700 megawatts of energy storage by 2035. And this is all necessary for decarbonization. Okay. Let's talk a little bit about one of our stationary battery energy storage pilot projects. We call this BESS 2. That's battery energy storage system number 2. This is one of the 3 pilot projects. It was installed in Hanover County. This is a lithium ion phosphate battery. LFP is the chemistry. And the size of it is 2 megawatts, 4 megawatt hours. So you'll always see a peak output with a battery, 2 megawatts, and then you'll see a time duration. So in this case, I can actually inject 2 megawatts for 2 hours onto the system. I take that 4, I divide it by 2, that's where I get it. This project is in service. We energized it Q3 of last year. And some fun facts, it's 2 40-foot by 8-foot enclosures. Each enclosure has 2,904 cells for a grand total of 5,808 cells total. And this has a primary application of peak shaving to defer substation transformer upgrades. So let's talk about that a little bit. So what is peak shaving? And I really want you to think about that PJM load curve. And if you look at that top blue curve, it almost looks like that sinusoid, just a smaller version of the PJM load curve. Well, this is the load curve of one transformer that is on our system. And just to go to the basics, like what is a transformer? So there's really 2 power systems out there. There's the bulk electric system and there's the distribution system. So when you're driving down the road and you see those massive transmission towers, that's the bulk electric system. Hundreds of thousands of volts, 500,000 volts, 765 kV, 230,000 volts, etc. But then there's a layer of power system underneath that called the distribution system. Those are the wooden poles that you see driving down the street and those power lines. And those are wheeling power to neighborhoods, factories, stores, etc. So the interface between them is a transformer, right? And transformers are in place to step high voltage from the bulk electric system down to low voltage. And the reason we have that high voltage is because the higher the voltage is, the lower the losses are on the system. So as we're wheeling that power from far away at a generating plant, we want to minimize the losses. So that way, we wheel the power with a transmission system. But every transformer, just like that PJM curve, has a load to it, right? So those wooden poles that you see leaving the chain link fence substations with the big gray boxes at them that have the Dominion Energy signs or the other utility signs where you're from when you're driving down the road, those big gray boxes are transformers, and all of them have load tied to them. Load is the houses and the stores that are hooked up to them. And if we zoom in on the load characteristics, what we'll see is that cyclic nature. We'll see that local minima, and then we'll see the maxima. So that's where battery energy storage comes in. And that's really the fascinating thing that these devices, what they can do. we can park a battery energy storage system just downstream of the transformer, and we can start to discharge the battery right at peak. So that's the lower, I guess it would be cyan curve. And then this is Dominion Energy's first peak shaving event with our pilot project. So on November 17th, 2022, we began to discharge the battery, and what it ended up doing is it clipped the peak off of the transformer. So imagine, go ahead. Hello? Somebody have a question?
No, we just had an open mic. Go ahead, Jerry.
Okay. So what this did is it shaved the peak off of the transformer. And what this does, we call this a non-wires alternative solution. And why do we call it that, right? So as population densities grow in an area, the utility will receive more load on its substations. And that's, neighborhoods going up, new stores coming to the area. And ultimately, the transformer that's serving the load will reach a point that it overloads. Power system planners are looking and they're watching that. And in the past, their only trick was to really split circuits out or bring in a bigger transformer or bring in an additional transformer. But now what we can do is we can park a battery energy storage system just downstream of the transformer, and we can charge that battery, during this low load period. And then we could be ready to dispatch the power during the high load period and ultimately take the load off of the transformer. Now imagine if this was wide area deployed on the system. This would give the utility something that they've never been able to do, which is control our power demand. PJM is sitting there and they are bringing those generators online to meet the RTO load curve. And sometimes they're just sitting back and watching load go up based on a prior day's forecast. But sometimes that forecast gets missed, and sometimes we get into emergency procedures because we don't have enough generation online. Well, if these were wide area deployed, this would give the utility what they've been looking for the past 100 years, the ability to control the power demand. Okay, so looking at Hanover, some eye candy from the field to see what these different components look like. So the middle photo is really what these Connex box containers are sitting on. So it's just different footing types. Sometimes it's a concrete pad, sometimes it's pylons drawn into the ground. And then the energy storage system is really a tractor trailer with a bunch of batteries on the inside of it. In this case, we have the inverter system and then also the step-up transformer to get the power back out onto the grid. Probably a little bit easier to see how the system works looking at the outline drawing below. So we got enclosure 1, enclosure 2. Those are the 40-foot by 8-foot containers. Then the DC power leaves the enclosure, it comes up and hangs a right. Each of them have their own bidirectional inverter. Remember, that's taking DC, converting it to AC when discharging, or taking AC and rectifying it to become DC for charging. I leave there and I go to a metering cabinet. That metering cabinet allows me to measure the power output or the charging input to feed that back to the control system to tell this thing whether to charge or discharge. Then I leave the metering cabinet and I go to a step-up transformer. The reason the step-up transformer is there is to convert the power to the voltage levels that are needed to inject back onto the grid. So I'm leaving the batteries at 1,000 volts DC, and then I invert that DC to become 480 volts AC, and then 480 volts AC gets stepped up to 34,500 volts DC to get injected back out onto the grid. Okay, and finally, we get to the GPODS project. Now that we've had a little bit of background on what battery energy storage systems are and why they're important to utilities. So the GPODS project is a pilot project involving Dominion Energy Virginia, the All Hazards Consortium, and the Virginia Department of Emergency Management. We are seeking funding through the FEMA BRIC grant, where the BRIC grant is Building Resilient Infrastructure and Communities. For this project, we will use mobile energy storage to provide grid support during normal conditions, similar to what the Hanover Battery Energy Storage System pilot project is doing. And then we will also deploy these mobile batteries to 7 predetermined locations to provide backup power during a natural disaster or a catastrophic event. So ultimately, what we're trying to do is develop a program that improves reliability to our distribution customers, but also provides additional grid support when we're not using the GPODS for the primary application. So how will the GPODS work? Oh, sorry, one second. So how will the GPODS work? So you see a picture of the GPOD in the lower left-hand side, and it's really Hanover, the pilot project on a trailer. Starting out on the left-hand side, we have the battery energy storage system. In this case, it's a 500 kilowatt, 1,000 kilowatt hour. So I could do 500 kilowatts for 2 hours with this system. Then I have a DC breaker, the bidirectional inverter. That's what's, again, converting the DC to AC during discharge, or the AC to DC during charging. I also have a transformer that is converting the output power to, in this case, 208 volts, 120 volts AC, which is compatible for the downstream building that we see. And then one important piece that we have off to the right of the trailer is the generator tap box, or cam lock connectors. And what we're going to have to do to deploy this project is we're going to have to permanently retrofit each of these sites with an additional switch, but also this green tap box. This will be cut into the existing infrastructure that is serving each building. So each building, power comes from the substation, it goes to a substation breaker, and then typically what you see is a pole mounted or a pad mounted transformer that provides power directly to the end user, which in this case is a building. So what we'll end up doing as part of the project, we will cut in these switches, and we will cut in this cam lock box where we can pull up the trailer, and then we can connect a cable from the generator tap box to the customer tap box. So here we are in normal lineup again. The substation is providing power through the switch that we can't cut in to the end user, but then during emergency conditions, or if we have a fault on the line, we can switch the switch to the emergency source to provide power from the GPOD. And the one nice thing about this is generators are expensive, and this allows the resource to be shared between multiple locations. Power outages tend to not be widespread. They tend to be congested into small areas. So what this allows you to do is not necessarily equip the site with a generator that may run once every couple of years. You can use the resource for grid operations when they're not needed for emergency backup, and then Dominion Energy could deploy them when that power is needed. Okay. And then a little bit more, a couple tidbits on how the project will work. So we're looking at, a sketch of one of our site buildings. We ended up choosing 7 sites, but actually 8 locations. One of our locations is a high school that is used for emergency storm shelter, etc. And there's actually 2 feeds into the location. So that's why we have 7 sites, but 8 locations. All of these sites were pre-screened through engineering analysis. And that's a real important piece to this, because the GPODs themselves have a finite amount of power. We couldn't hook up to, a major city and power a whole city with a GPOD. We really need to study the power profile, the power consumption of the building, and see if it's a good fit, because we really don't want to have to swap the GPODs out more than once a day. So how this really all worked out is All Hazards Consortium and Dominion Energy worked with VDEM and local emergency managers to identify buildings and sites within their territory that were important during an emergency. My engineering team pre-screened these sites to see which were a good fit for the project. We looked at about just over 30 sites, and we down selected to 7 sites, 8 locations for the pilot project. And then, like I said, we will move out to each of these sites. This is the power coming into the building, this TX, that's an abbreviation for transformer. And then really the power is kind of coming off the utility into the transformer, and then it serves the building. We will retrofit that transformer with the cam lock connector and the switch. And then, those sites that have a nice big parking lot, we can pull the GPOD up into, and a human will connect the cables from the GPOD generator tap box to the cam lock connector that is permanently located at the building. So just to see in reality what these really look like, this is 2 vendors that we're looking at for the project. These are both lithium iron phosphate batteries, a little bit different in sizes. One, for vendor 1, has a peak output of 500 kW, but at a duration of 1 megawatt hour or 1,000 kilowatt hours. The other one can do a peak output of 1,000 kilowatt hours. And basically all that is it could take 1,000 kilowatt punch, but it could only serve it for an hour. Some sizes on the containers. There's a vast array of different voltages that these can put out, so we can match them to our customers. All of them have a human machine interface for controlling the system. We should be able to pull the trailer up, and I'd say within less than 5 minutes be able to hook up and provide power to the site. And then regarding safety, there's a lot of fire detection, suppression, smoke and gas detectors, and then your traditional electrical isolation devices like AC fusing and AC breakers, etc. Okay, so some challenges faced with the project. The first and foremost is probably there's a limited number of qualified vendors out there supplying mobile storage. And I do say qualified. The battery energy storage sector is an emerging market, and new players are coming almost on a monthly basis. So as part of this, we researched the industry to see what our qualified vendors would be, and we down selected to 2 that could meet our needs. Another challenge is the GPODs will have to meet, actually they must meet Dominion Energy's fire protection standards. Most specifically, we are going to require that these devices are certified to UL 9540 Alpha, NFPA, which is National Fire Protection Association Code 855, and UL 1973. And this is really to ensure that Dominion Energy is honoring its outstanding safety record and making sure that nobody gets hurt. Anytime that you're dealing with an electrical energy device or stored energy, there is always inherent risks. So my engineering team is in place to make sure that we deploy the proper engineering safeguards to make sure that our customers and the public are safe. We will also, one challenge is, as a result of understanding the design in detail, we will likely ask our vendors for customized engineering safeguard features, and what that will end up doing, it may lead to procurement delays associated with getting our hands on the equipment. Why is safety our #1 goal? Our safety is Dominion's #1 goal, because if we don't do it right, bad things happen, right? And not only with battery energy storage, but with any power device. Our end users are not experts of electrical energy like we are, and it is really up to us from an ethical standpoint to make sure that everything is safe. These are a couple examples of some bad days for energy storage. Energy storage, if it is significantly damaged or significantly overused, can turn into a fire or a thermal runaway event. In the worst case scenario, you could have an explosion. Energy storage is safe, though, I will say that. It just has to be done right, and the proper engineering resources need to be aligned to the project to make sure that that safety culture is maintained. Okay, so the project over the next 5 years. So right now we're focused on deploying the GPODs to these 7 sites, 8 locations, and we will frame the project or the entire program based on this initial pilot project. And I think from that point, it will really be easy to scale. I mean, the model is essentially, you know, Department of Emergency Management works with local emergency managers to understand which sites are important for emergency conditions. And if they do not have an existing diesel generator or backup generator, we would screen them to see if they are a good fit with a GPOD. Then we would permanently retrofit those sites with a switch and a cam lock connector. And then, you know, as those sites grow, we would have to buy more GPOD trailers for the project. So I think that it'll be very easy to scale this now that we understand what the model is for the project. And then the next 5 years, you know, mobile energy storage could really be used for wide area outage restoration. So if you kind of think about the different characteristics on the system, a lot of times you're seeing power poles that are going to neighborhoods, and then there's a pole drop and everything is buried inside of the neighborhoods. There's 1 or 2 locations that are providing power to a huge community of, you know, a couple hundred homes. That's a perfect application for a GPOD. So we could cut in the switch in the cam lock connector, and then during our outage restoration process, if we had a hurricane or something blow through Dominion's territory and we couldn't get to a neighborhood for, you know, a couple days, we could have mobile energy storage there to you know, carry them until the proper repairs could be made to the permanent lines that are feeding the neighborhood. Okay, so that's the project in a whole, and you know, summary of energy storage and why energy storage is important to utilities. I will take any questions that anyone has at this time.